Helicopter flying. 4.1 Helicopter components, sections, and systems. Exploring the helicopter's rotor system. At the heart of every helicopter lies the rotor system, orchestrating the enchanting dance of flight, a trio of components, mast, hub, and rotor blades, each playing a vital role in this aerial performance. Imagine the mast as a robust backbone, lifting and supporting the rotor system. At the top, the hub gathers rotor blades, the unsung heroes creating the magic of lift. Rotor systems, akin to dance styles, come in three types: semi-rigid, rigid, and fully articulated. Modern engineering introduces a fusion, the bearingless rotor system. Semi-rigid harmony. In a semi-rigid duet, two blades elegantly connect to the hub, swaying and tilting in a dance choreographed by teetering or flapping hinges. The result? Graceful flapping and pitch changes. An underslung rotor is a balancing act, where the center of gravity hangs below, minimizing lead or lag forces. It's a delicate dance in the sky, ensuring harmony during the rotor's flapping. Enter mast bumping, the villain of this ballet. Excessive flapping can lead to rotor flap stops colliding with the mast, a risky encounter to be avoided at all costs. Flapping angles, the key actors, vary with speeds, rotor revolutions per minute, altitudes, loads, or turbulence. Adapting the dance moves ensures the helicopter's graceful navigation. Beyond spinning blades, the rotor system is an intricate symphony, managing lift, pitch, and elegant dance moves in the vast sky. Understanding these dynamics is the key to a safe and graceful flight. Diving into the rigid rotor world. Imagine a rotor system that's both mechanically simple and structurally intricate. Meet the rigid rotor. Here, blades stand firm, rooted in the rotor hub, bending to the whims of aerodynamics without the need for flapping or lag hinges. The rigid rotor system opts for structural elegance, bypassing hinges in favor of bending blades to accommodate movements. It's like a dance where simplicity meets aerodynamic finesse. This rotor style is responsive and less prone to mast bumping, thanks to a solid attachment to the main rotor mast. The rotor and fuselage move together, minimizing oscillations. Plus, shedding weight and drag from the rotor hub grants it a nimble and precise control. Say goodbye to complex hinges, maintaining the rigid rotor system is a breeze. It combines reliability with simplicity, embodying the best of semi-rigid and fully articulated systems. In turbulent skies, the rigid rotor may trade some elegance for cabin vibrations. Without hinges to absorb large loads, the vibrations become more noticeable, a small compromise for its structural simplicity. Adding a twist to the rotor narrative is the bearingless rotor system, a sibling to the articulated rotor. No bearings or hinges here, just a graceful reliance on blade and hub structure to absorb stresses. It's rotor evolution in the spotlight. Fully articulated rotor system. Picture a helicopter in flight, a symphony of blades responding to the subtle cues of the pilot's commands. This ballet in the sky is made possible by the fully articulated rotor system, a masterpiece of aerial engineering. As the pilot guides the helicopter through the air, the cyclic control comes into play, orchestrating a harmonious dance of lift and balance. The blades, like skilled dancers, elegantly flap upward, their motion gracefully balanced by the centrifugal force. Imagine an ice skater gracefully spinning, adjusting her arms to control the speed of her spin. Similarly, the lead or lag hinge in the rotor system ensures smooth and controlled transitions, maintaining the balletic grace of the helicopter's flight. In this aerial dance, conservation of angular momentum is the unseen choreographer, aligning control inputs with the aircraft's graceful movements. Modern elastomeric bearings take center stage, replacing traditional metal bearings, providing reliability and visible wear solutions. This airborne symphony, conducted by the fully articulated rotor system, transforms a helicopter into a virtuoso performer, executing mesmerizing maneuvers with precision and responsiveness, a true dance in the sky. Tandem rotor. Ever wondered about helicopters with not one but two sets of rotating blades? Enter tandem rotor helicopters, featuring two large horizontal rotor assemblies and a smaller tail rotor. This configuration, seen in Figure 410, utilizes counter-rotating rotors to nullify each other's torque, allowing for increased weight carrying capacity with shorter blades. Coaxial rotors. Now, picture a coaxial rotor system, a pair of rotors turning in opposite directions on the same shaft. This design, showcased in numerous Russian helicopters and the Sikorsky Experimental X-2, eliminates the need for a tail rotor or other anti-torque mechanisms, overcoming the challenges of dissymmetry of lift. Intermeshing rotors. Next up is the intermeshing rotor system, featuring two rotors turning in opposite directions with blades intermeshing without colliding. This design, seen in helicopters like the Cayman HH-43 and K-Max, eliminates the need for an anti-torque system but comes with the trade-off of reduced rotor efficiency. These unique rotor configurations showcase the innovative approaches in helicopter design, each offering distinct solutions to the complex challenges of lift, torque, and efficiency in the dynamic world of aviation. Now let's discuss the engines in the helicopter. Reciprocating engine. Small helicopters, especially in training, often rely on reciprocating engines, also called piston engines. They're chosen for their simplicity and cost-effectiveness. For more details and illustrations, check out the Pilot's Handbook of Aeronautical Knowledge. It's your guide to understanding these engines that power the rotorcraft. Turbine engine. Turbine engines, found in many helicopters, offer substantial power for their size but are generally more expensive to operate. Unlike airplane applications, the helicopter's turbine engine primarily expels exhaust gases without contributing to forward motion. About 75% of incoming airflow is dedicated to cooling the engine. The gas turbine engine consists of a compressor, combustion chamber, turbine, and accessory gearbox. To prevent debris ingestion, various filters are employed. However, pilots should remain vigilant, especially in environments prone to debris like sand or dust. The compressed air undergoes combustion, and the resulting gas drives turbine wheels, powering the compressor and accessory gearbox. The generated power is transmitted to the main and tail rotor systems through the freewheeling unit. Exhaust gases exit through an outlet, with temperature measured by terms like interturbine temperature, exhaust gas temperature, or turbine outlet temperature. See figure. It provides a visual reference. Compressor. In a turbine engine, the compressor can be either axial or centrifugal, or a mix of both. Axial compressors have rotating blades, rotor, and stationary vanes, stator. The rotor acts like a fan, drawing air in, while the stator slows it down to increase pressure. Multiple rotor-stator pairs create pressure stages. Centrifugal compressors consist of an impeller, diffuser, and manifold. The impeller speeds up the air, and the diffuser slows it down, leading to high-pressure air. The manifold distributes this to the combustion chamber. Surge or compressor stall is a hiccup in airflow that causes pressure issues. Activating the bleed air system can correct this by releasing excess pressure and allowing more air into the compressor to keep things smooth. Combustion chamber. In a turbine engine, combustion is continuous once ignited. An igniter plug starts the process, and interruption in fuel or air causes a flameout, requiring a restart. Some helicopters have auto relight for automatic ignition. Turbine. The two-stage turbine includes gas producer, N1 or ING, and power turbine, N2 or NP. In a fixed turbine, turboshaft, they're mechanically coupled on a common shaft. In a free turbine, they're independent, allowing free rotation. Combustion gases pass through N1 to drive the compressor and N2 to power the gearbox and output shaft. Accessory gearbox. The accessory gearbox contains gears driving various helicopter components. N1, gas producer, powers the engine cycle components, while N2, power turbine, drives the main rotor, tail rotor, and other accessories. This design makes the engine self-sustaining. If you click like and subscribe and leave a comment, we will provide a coupon for a free PDF download, one of 9 ebooks. However, each individual can only download up to 1 out of 9 ebooks for free.